So now we're going to look at the Riesz representation theorem as it applies to the space of polynomials. So if we take the continuous functions on -1 to 1, this is an infinite dimensional vector space. And in particular, if we're thinking about the real coefficient polynomials of degree n as being a subspace of the continuous functions on -1 to 1, it's clear that the cosine is never in there. The cosine can be written in terms of a power series, but that's like an quote-unquote infinite polynomial. So for no finite n is it actually equal to that polynomial, because there's always the lingering terms down at the end, right? Nonetheless, by the Riesz representation theorem, there's going to be some polynomial Pn such that if we use the cosine to define this linear functional, so this is a well-defined element of the dual of Pn, well, then by Riesz representation theorem, that means that there's some actual element of the inner product space such that it's going to be equal to the inner product against that element. So this is a crazy thing here. This is like saying that from the point of view of Pn, Pn cannot distinguish between this cosine function and this polynomial function. So that's pretty loopy, pretty weird. So let's see. So this is only possible, right? Because the dimension of Pn is finite. Otherwise, this kind of thing wouldn't be able to happen. So let's see. So now we're going to work out in detail. This is actually example 644 from the text, and we are going to find a second order polynomial such that this this functional right here, this integral against cosine, is actually can be given as the inner product against q. So we're just working in the n equals 2 case here to keep the arithmetic from getting belligerent. And so we're going to use the orthonormal basis that we calculated in the previous worked example. So this is the one where we've got E0 is going to be 1 over root 2, and then E1 is going to be square root of 3/2 times x. And then E2 is going to be square root of 45 over 8 times x squared minus 1/3. So that'll be our orthonormal basis. And then if we look back at the proof that we used for the Riesz representation theorem, that tells us that the isomorphism where phi maps to inner product against phi ek conjugate ek, that gives us our isomorphism, right? So we can define u to be, in this case we're only going up to the n equals 2 case, so we've got phi 0 E0 plus phi E1 conjugate E1 plus phi E2 conjugate E2. So let's see. So plugging in E0 into our phi functional, we have -1 to 1, 1 over root 2. There's our E0, and then we've got cosine pi t dt, and then this is going to be multiplied by E0, which is 1 over root 2. So and now here everything is real valued, so we don't actually need the conjugate. I guess here I'll put the conjugate in purple just to indicate, like, normally this would be here, but since everything's real valued here, we don't actually need it. And then so this part right here, this is phi of E0, well, conjugate ish, and then here's E0 off at the end. Okay, and then we have integral -1 to 1 of root 3 over 2 t cosine pi t dt. And so again, this part here is our phi E1 conjugate, and this part here is our E1. And then lastly, we've got the integral -1 to 1, and then that ugly guy, square root 45 over 8 t squared minus a third cosine pi t dt, and then square root 45 over 8 x. So that's not x, what am I doing? That's x squared minus a third. There we go. Okay, so, and that's our E2, and this is our phi of E2 conjugate. Okay, all right. And then it's time to do calculus. Calculus. And after a bunch of calculus, you end up with minus 45 over 2 pi squared times x squared minus 1/3. Okay, and so this is indeed a polynomial. Oh, and I just realized I'm calling this u. I don't know why I'm calling this u. I said I was going to call it q, so it's q. So for this polynomial here, it turns out that this crazy thing is true, that the integral from -1 to 1 of a polynomial cosine pi t dt is equal to integral from -1 to 1 minus 45 over 2 pi squared x squared minus 1/3 times oops, I put it on the wrong side. There we go. Okay. Now, if we go on to, if we put in a polynomial here that has degree 3, maybe the equality breaks. In order for that, you would have to go back and you'd have to add in some third term over here and put that corrective term in there, and then you would get a polynomial that it would work for, and so on and so forth.